you've been given a volume and a concentration of acid, and you have been given a volume and a concentration of base, and all that they want is the H plus in the acid and the OH minus in the alkali. There's only one hydrogen in here, and there's only one OH in there, so it's not particularly weird or strange or anything. You literally just have to work out the number of moles in each of the solutions, and there's a 1-to-1 ratio. So the number of moles is equal to concentration times volume. For the acid, 0.15 times 0.5. Obviously I had to change that into decimeters cubed, and you get 0.075 moles. The next one, exactly the same formula, slightly different numbers. 1 decimeter cubed, and you get 0.05 moles of sodium hydroxide, but that's the same as the hydroxide as well, because NaOH is to OH as 1 is to 1. HCl is to H plus, or if you prefer H3O plus, as 1 is to 1. So there's no reason to change those numbers. So there are your answers. What indicator would you use if hydrochloric acid is a strong acid, is reacted with ammonia, which is a weak base, and sodium hydroxide, which is a strong base? So in this case over here, you're going to land up with the acid winning the race, so you're going to get an acidic endpoint, and you need to use either methyl orange or methyl red. Either of those will change color in a slightly acidic medium. Here you're going to land up with a neutral endpoint, strong acid and strong base. You could have told me either bromothymol blue or litmus, I would have accepted. Does ammonia act as an acid or a base in the above reaction? Well, let's do our little acid-base pairs. We have got a proton acceptor over here, so that's base 1 turning into acid 1, and acid 2 going into base 2. So is ammonia acting as an acid or a base? It is a base. Why? Because it is a proton acceptor. Write down the conjugate acid-base pairs for the reaction. So NH3 and NH4 plus is your one acid-base pair, and your other one is H2O, OH minus is the other pair. Write down the conjugate base of water. Water, once it has lost a proton, so in other words, it's an acid. If you're looking for its conjugate base, it has to behave as an acid, so it's a proton donor and becomes OH minus. And HCl donates its proton and becomes Cl minus. What are the conjugate acids? Now we need this water to act as a base. In other words, it needs to be a proton acceptor. So it's H3O plus, and the ammonia NH3 accepts a proton and becomes NH4 plus. Now we've got to complete these reactions using chemical formulae. So it's hydrochloric acid plus magnesium. It's a metal plus an acid will give you a salt plus water, plus hydrogen. Now your salt you actually need to work out. So you're going to say magnesium has a valency of 2, chlorine has a valency of 1, hold hands, chlorine has a valency of 1, and then you get MgCl2. Then you still need to balance that by putting a balancing number in. Next one is a metal, lithium, plus phosphoric acid, H3PO4, and phosphoric acid and lithium are going to form lithium phosphate as a salt and hydrogen. So it's a metal plus acid gives you a salt plus hydrogen. I need to work out this lithium phosphate. Lithium has a valency of 1. Phosphate as a group has a valency of 3. So I'm going to require 3 lithiums to go with 1 phosphate. So it's Li3PO4. I then need to balance that equation as well. So I'm going to start looking at the fact that I am going, if I put a 2 over there, a 3 over there, I'll end up balancing out the lithiums. There's a problem with the hydrogens. I'm going to need to put a 3 over there and a 2 over there. That's going to involve putting a 2 over there and then a 6 in front of the lithiums over there. And if you count it up, you are going to land up with a balanced equation. The next one that we've got is sodium carbonate. So sodium carbonate is Na2CO3. Again, I need to work that out. Carbonate's got a valency of 2, sodium's got a valency of 1. And nitric acid, HNO3. When I've got a carbonate and acid, I get a salt, which is going to be sodium nitrate. Sodium has a valency of 1, nitrate has a valency of 1, plus water, plus carbon dioxide. I then need to get that to balance out, and I land up with the balancing numbers in like that. Finally, we've got potassium hydroxide. Potassium hydroxide is KOH, valency 1 for potassium, valency 1 for hydroxide. And sulfuric acid, H2SO4, is going to give me a salt, potassium sulfate. Potassium has a valency of 1, sulfate has a valency of 2, and water, H2O. And that turns out to, it's going to need, we need a 2 over there, it's going to need a 2 over there, and then we've got a balanced equation. Notice that you actually have to puzzle these out. You can't just suck your fingers and hope that you're going to land up with the right formulas. A certain mass of sodium carbonate is dissolved in a certain volume of water. What is the concentration of the solution? I first need to get the number of moles of sodium carbonate. So number of moles is mass over molar mass. What is the molar mass of sodium carbonate? 23 plus 23 plus 12 plus 16 plus 16 plus 16. And I land up with 106. So it's 5,3 divided by 106. And my moles is 0,05. Concentration is number of moles divided by volume. You've got to be writing these formulas down, because if you don't write the formulas down, I can't give you marks if you get anything wrong. And I'm going to have to start getting stricter and stricter with that. It's not whether I can see what you're doing, it's whether you've written down what you're doing that gets you your marks. That turns out to be 0,2 moles per cubic decimeter. Decimeter minus 3. Per cubic decimeter, there has to be a little minus on that over there. Sodium carbonate is neutralized by hydrochloric acid, and we've given the balanced equation, which is quite good news. If 20 centimeters cubed of the acid solution is neutralized by a certain 25 centimeters cubed of sodium carbonate, calculate the concentration of the sodium carbonate solution. This is great. It's 2 liquids. They both have a volume given to you. You can literally use the monkey see, monkey do formula. So it's number of moles of acid over number of moles of base, concentration of acid, volume of acid, concentration of base, volume of base. Now remember, this equation does not appear on your information sheet. Don't stuff it up. Otherwise, go back to the basic principles where you first get the number of moles, then work out the mole ratio, and then go back to find the concentration. But if you can use it, it is a quick and easy way. Number of moles of acid, 2. Number of moles of base, 1. Concentration of acid, 0,5, it's given to you. And the volume is 0,02, but you don't have to change it. You can just leave it as 20, because if you use this formula, you don't have to change the units, because it's exactly the same units and it's going to cancel out. And the concentration of base. Your concentration of base is going to turn out to be 0,2 moles per cubic decimeter again, by coincidence. Looking at the multiple choice, which of the following substances is an ampholyte? In other words, it can donate and receive a proton. That's out altogether. It doesn't even have a proton in it. The hydroxide ion is able to go OH minus, and then if it donates its proton, it becomes O2 minus. But that isn't. This is a proton acceptor by nature. It doesn't donate its proton at all. So this is a base, pretty much, and it's difficult to think of it as an ampholyte. This is an acid, pretty much. You can't really get H4O2 plus as it gains an extra proton. That's not going to happen. This substance over here, let's watch it and see if it does something obvious. Firstly, if it gains a proton, it becomes H2SO4. That's called sulfuric acid. We like that. And if it loses a proton, it becomes SO4 2-, which is the sulfate ion. That looks like a very likely amphilytic substance. Ethanoic acid is a weak acid. Why? Weak acids form few ions in solution. So let's see. Produces few hydronium ions in an aqueous solution. That sounds like a good idea. Can react with a strong base, can react with a weak base. That's rubbish. Anything can react with anything. Usually is greatly diluted with water. Dilution is not the same as strength, and therefore weak and strong and diluted are not the same thing either. So the only option here is that we've got very few hydronium ions forming. Pure water is neutral. Why? Because it contains polar water molecules. Well, that's true, but it's got nothing to do with its neutrality. Contains no ions. That's not true. It's because the H3O plus ions are exactly equal to the OH minus ions that you actually have neutrality in water. Which are the two acids in the following reaction? You'll recall that needed to move to there. And we have got a proton donor, which turns into that proton acceptor. We've got this proton acceptor, which turns into this proton donor. So the two acids are HSO4- and H2O, and that lands up being answer C. Which one of the following pairs is an acid-base pair? That means there's one hydrogen between them. Here you go. When that proton is donated, you land up with the other substance. This hasn't got any protons in it, nor is that, so that's a load of rubbish. And these two are not an acid-base pair at all. If H3O plus loses that says H3O minus anyway, which makes it even less likely, but if H3O plus were to lose a proton, it would become H2O, not OH minus. I suppose you could then go to the next step and do that, but it's not an obvious acid-base pair. So our only correct answer is B. Then 8.6, I've been given a solution over here of sodium sulfate. Sodium sulfate is Na2SO4, and they would like to know the concentration of that. So I need to say concentration is equal to number of moles divided by volume. Before I do that, I need the number of moles is equal to the mass. Oh no, they've given me the number of moles. How cool is that? So it's 0,5 divided by 0,5, and I land up with 1 mole per cubic decimeter. That was pretty easy. If they asked me for the sodium ion concentration, remember for every 1 Na2SO4, I have got 2 sodium ions, so I would need to double that. The label on a flask reads the following. This can be concluded that, what have we got? We have got 1 mole per cubic decimeter, and there's aluminium ions that they're asking about here, and sulfate ions. So I would have, instead of, it would be 2 moles per cubic decimeter of aluminium ions and 3 moles per cubic decimeter of sulfate ions. So if I had 0,5 moles of sulfate, I'd need to be in 3 decimeters cubed of solution. If I had, sorry, let's just unpack that a little bit, Al2SO4 3 to Al to SO4 2-. I am 1 is to 2 is to 3. And it turns out that the only one of these that works out is that I've got 2 moles in 1 decimeter cubed of aluminium 3+ ions.